He's a professor at CNRS in France, in the Laboratory of Signals and Systems of Paris-Saclay University. He got his PhD from University of L'Aquila in Italy in 2007. Among many other services, he's now the editor-in-chief for the IEEE Communications Letters. He's also a founding member of the ETSI Industry Specification Group on RIS. He has many awards. I've only picked maybe a few recent ones. So 2021 Eurosep Best Paper Award, 2022 IEEE ComSoc Outstanding Paper Award, 2022 Michael Monpetit Prize, and I think you guys also won the recent prize for TCOM, right? The best TCOM paper. Thanks. So Mark has been doing a lot of work in reconfigurable and intelligent services, and most recently in SIM, and we look forward to hearing from you, Mark.
Okay, thank you very much. Thank you very much. It is working? Okay, yes. So thank you very much, Chris, for the nice introduction and for organizing and putting together this wonderful event also with fun. So I'm very glad, to be here, and also thanks for pushing this topic, which is very interesting. You started working on that a long time ago, so I think it's very promising. So today I will take this one.
Yeah, I think that one is not working.
It's not working. Okay.
Sorry.
Thank you. Better? Yeah, much better. Yeah, thank you. So I would say so I will take basically the perspective of essentially looking at ISAC, but from the point of view of these reconfigurable intelligent surfaces, what they can do, what they cannot do. And today I will primarily introduce this new technology, which I'm very much excited about. It's very recent, and for me, it could be a nice platform for integrating communications, computing, and sensing. And I will try to touch upon these three aspects today. Actually, this is kind of two-part tutorial that we have been giving with Bruno. So Bruno has already told you a few things, and I will try not to repeat the same things, but I will tell you a few things with my own words. Okay. So that's basically this talk. First, a very quick and brief recap on programmable metasurfaces, just to make sure that I explain you my language, my terms. Then we jump into the SIM or SIM, and we will try to see what it is, why this technology has been introduced. Also, we'll try to complement also what Bruno said about the comparison between the SIM and beyond diagonal refracting surfaces, metasurfaces that we are working together, what kind of benefits you can get from it. And then I will show you some examples of how this platform can be utilized for doing computing and sensing in the web domain. And I will explain this. And then, thanks to some collaborators from China, we built what we believe is the first prototype of this technology for applications to communications and sensing. So I will show you experimental results for communication and sensing. This paper was submitted to GlobalCon just a few days ago. So it's the first time that I'm going to show this kind of results. Okay. So, let's just set this scene. So, all the times that I will be talking about a metasurface or programmable metasurfaces, this is the kind of figure that you can keep in mind. So, we have a few antenna elements in red and electronic circuits. Okay. So, programmable because we have this electronic circuit. So, otherwise, it's going to be static. Today, my main job in this field is primarily to work at the interface between electromagnetics and communications. Today, I will not tell you anything about the electromagnetics. I will take just a pure communication perspective. And the way that we model usually the pair antenna elements, electronic circuits is like this. It's a phase shifter. We can control in general the phase. Sometimes we control the phase, the amplitude, but in general, what we really care about is the controllability of the second phase. Okay. So in wireless, fundamentally, the problem is very simple. We want to maximize objective function, which can be the SNR in a very simple problem, and we want to play with these reflection coefficients or transmission coefficients later on. And the problem is extremely complicated, especially because in general, the feasible set is not convex. So you will find a bunch of papers on trying to tackle this problem with models that are more or less simple, more or less complicated, but the problem is quite complex. Okay, that's basically what people do in optimization theory. So, but if you take any papers in optimization, you really don't understand. It's purely numerical, so it's very difficult to get any sort of insights of how we should optimize these phases. But if you go back to physics, there are many cases where things are extremely simple. Okay, maybe it's too much simple, but I mean, let's look at this. If you really want to steer one beam from one direction to another, from the very fundamental point of view, what you want to do is to phase modulate the signal that illuminates that surface. And the law that governs, in fact, this operation is the generalized Snell law, and it tells us that whatever your angle of incidence is, if you want to have a given angle of reflection, this is actually determined by the first order derivative of the phase that you apply to that surface. It's extremely simple. So if you have a linear phase shift, just a simple linear phase shift, you know exactly how to compute this phase shift, and you can optimize the slope of this phase shift. So alpha, in this way, you basically see that your desired angle of reflection is exactly, your angle of reflection is exactly this one. This is what you put here in this alpha. So, I mean, in many cases, things are extremely simple. Of course, it is a single user setting. If you go to multi-user with interference, etc., you need to go solve the problem numerically. But I mean, this allows us to get at least some intuition. Okay. Okay, so the concept here is that when you cannot communicate with a user, you want to recycle reflections in a smart way such that they become useful for you. Okay, that's a little bit. So now, if you want to know more about this technology from the very beginning to today, there is a paper that was recently submitted a few months ago and was also accepted. The proceeding of the IEEE is a special issue on 6G, and I think that many others here contributed to that special issue. But here also we would like to acknowledge many of the all the authors that are there, because it's thanks to all of them that this technology a few years ago started being, became quite popular. Okay. So now let's go into the main topic. What is this stacked intelligent metasurface, and what basically we want to do with it, or we can do basically with it. So basically, a stacked intelligent metasurface, as the name implies, is a bunch of surfaces, okay, one after the other, and the signal basically propagates from the input and goes basically to the end. And you can do many things with this kind of technology. So for each layer of this structure, you have a programmable metasurface. So it's a multi-layer programmable metasurface, which does not work in a reflection mode if you're working on RIS, but work in refraction mode. So it's a transmissive structure. Okay. It resembles a deep neural network. Okay, and in fact, there are papers in China that proposed this structure, not in the way that I will show it to you, but as a way to implement neural networks in the wave domain, to avoid to do neural networks in the digital domain. Okay, so essentially, this SIM is exactly this kind of structure. There are differences that I will tell you in a while, but so far, just to give you a visual idea. So why basically we want to have this kind of architecture? I will give you two possible views, or two possible views, and then a few. I will detail each of them. So the first thing is to utilize this as a replacement for a base station, to implement low complexity base stations. Okay. So let's see what the problem is. This is a conventional base station. The key elements are a very complex baseband processing unit. Then we have digital to analog converters, and then some phase shifters if we have an hybrid architecture. What you can do with SIM? With SIM, you could, in principle, this is the extreme case, you could completely remove the digital signal processing part. You just send the signal through the low resolution digital to analog converters. And then what you were doing before in the digital domain, now you're going to do it in the analog domain. It's like if you are swapping that baseband processing here and you move it here and you do it in the analog domain, so in the wave domain. Lower latency, lower complexity, and so on and so forth. That's essentially the reason why we want to go for this kind of technology. This is the conventional approach for a conventional base station. Now there is also a new generation of base stations, which is called holographic MIMO, where basically what you have a very dense number of elements on a substrate with some feeders, and this structure can be modeled as a continuous structure according to some homogenization models. What you do is just to stack many of these surfaces one after the other, and you can get the same principle. Okay, so it can be applied to both kinds of technologies. So what are the pros? The pros are that if you compare this architecture, this technology with full digital pre-coding, hybrid, and so on and so forth, you have that the number of RF chains can be reduced because you want to reduce the number of RF chains and capitalize on the large number of elements that you can put on these surfaces. So that's basically the trade-off. You can reduce the number of bits in the analog to digital converters, and the hardware cost is also reduced because you don't have many RF chains, digital elements, and also the energy efficiency is improved. Why? Because we know that the power consumption of ADC grows linearly with the bandwidth and exponentially with the number of bits. So if you can actually reduce as much as possible the number of bits, you gain a lot in terms of power consumption and complexity. Okay, that's essentially the main, in simple terms, the reason. So there is also another view. This is how it was proposed. You try to build a low complexity base station, but you can also try to utilize it as a refracting version, multi-layer refracting version of a reflective intelligent surface. Okay, it's gonna you can also use it for refracting intelligent surface. Okay, if you want. But so the concept is that now you cannot go through something, and you can put basically this device through, try to get some beamforming gain, and try to go through basically the window, try to go through the obstacle. For example, this can be utilized for outdoor-to-indoor communications in millimeter wave. People in China put this structure on a wall and try to measure how much power was received behind the wall in order to go through the obstacle to reduce the attenuation between these kind of people. So let me now tell you another view, which is related to what Bruno told you. So the bottom line is that I want to show you that SIM can be viewed as an approximation for beyond diagonal RIS with some pros and cons. Okay. It's not equivalent. There are pros and cons, as Bruno told you. And now we'll go in these details. So the typical scenario that we have for an RIS, for those of you who are working on that, so reflecting surface, the typical assumption is, and we have seen this in many papers, diagonal structure. Bruno told you this is what many people do, the vast majority of people do. And then we have the unit modulus constraints because we don't go to attenuate. So this is the perfect reflector. Okay. Now, instead of going around the obstacle, you can go through the obstacle, or you can go through the window through this kind of structure. So now this is not anymore a reflection coefficient; it's a transmission coefficient, and this in principle applies to every single layer that you have here. Okay. So now, from this is the diagonal structure that we have. Now, what we proved. And I will show you now the paper that from the information theoretic point of view, this design, so the diagonal design with unit modulus constraint, is not capacity achieving. Essentially, nearly passive, so a structure that does not amplify the signal, is not a structure that has a diagonal matrix, transmission coefficient or reflection coefficient, but it needs to fulfill this formula, which also Bruno showed you. Now, if you want to understand from the information theoretic point of view, which is the optimal phi to be utilized, what we should do is to solve this problem, which is the same as a Teladar problem that solved many years ago with an additional constraints that now we have this phi, which is a unitary matrix. If you remove this and you set this to a constant, this is equal, exactly the same as Teladar paper. So we just generalized a little bit Teladar paper, no more than that. Okay. Long story short, this problem can be solved. This optimization problem can be solved. And the solution, without going into the details, is that we can indeed compute the optimal matrix phi that maximize this capacity. And this matrix phi is not diagonal. So it's insane that if you consider these constraints here, because okay, this is not a complex constraint, we cannot do almost anything. We need to do it numerically. If we relax this and we try just to use the unitary matrix, we can get the solution in closed form, and this is true whatever channel model you have, because it comes from the singular value decomposition. So while a performance evaluation for RIS has always been a problem, because we don't have a closed form expression for phi, now we can use this as an upper bound and compare actual practical solutions to see how far we are from that. Okay. So, and essentially we go then that non-diagonal, beyond diagonal RIS should be the way to go, also from the information theoretic point of view. And Bruno has shown you very nice results in terms of signal processing performance, depending on the trade-off between circuits and so on and so forth. But this also comes from here. So now, what is the connection between beyond diagonal RIS and SIM? So SIM is a structure of this kind, where you can have here a metasurface with a diagonal response, another metasurface with a diagonal response, and then you go on forward with many layers. But between them, there is hair. And the signal, when it is emitted by this guy, there is the broadcast feature of wireless communication. So it's going to be received by all the elements, and so on and so forth. So you have a cascaded channel model that represents the end-to-end response of this structure, in which you have the metasurfaces with a diagonal response. But in between, the air applies a non-diagonal matrix. When you combine the product of many diagonal matrices with non-diagonal matrices, you end up with a non-diagonal structure. So SIM can be viewed as an approximation of beyond diagonal RIS, which is implemented by using diagonal metasurfaces. But there are some pros and cons. We'll tell you now in a couple of slides. So this also allows us to see a little bit the difference between beyond the SIM and the deep neural networks. If you use this model, which is the one that you will find in all the papers now, the few papers that exist, this is a linear model. So now, if you use this model, the main difference between SIM and DNN is that in SIM, there are we don't have no linear elements. We don't have activation functions. So we cannot do the same as DNN does today. But Bruno has showed you that the true model for an RIS or for a SIM or whatever it is not this one, which is a linear model, but is this one, which is a non-linear model, because the matrix of reflection coefficient S, scattered matrix, is inside an inversion function. This is a strongly non-linear model. So there are some linearities. The problem is, can we control them? That's another story. Okay. Okay, that's we don't know, but there are some linearities if you utilize the correct models. Okay, but this is completely unexplored so far. So that's essentially the connection. Now, if we try to compare these two guys, as also Bruno told you, the beyond diagonal RIS is one layer. So there are no attenuations. So you cannot do better than that, because you have the highest complexity. I mean, of course, you have a full circuitry. So all the elements are connected. You have only one layer, so you don't have the intra-layer propagation losses. Okay? That's the point. But with SIM, you have a reduced complexity and power consumption, because the number of tunable circuits is given by the number of layers multiplied by the number of circuits per layer. It's not given by the number of circuits to the power of 2 divided by 2. So, but it depends. So in principle, you cannot have many layers, so it should be less. So now, just to give an idea of the comparison, this is a paper that, an embedded paper submitted to SPOC with some colleagues and collaborators, especially the group of Edward Yorswick, who is an expert in energy efficiency optimization. And this shows the energy efficiency versus the power consumption of each RIS elements for multiple RIS implementations. You need to focus on two lines, the green line and the blue line. The green line is the diagonal RIS, and the blue line is the beyond diagonal RIS. There is a crossing point. Of course, I mean, if the power consumption of these elements is very low, beyond diagonal RIS is the way to go. Also from the energy efficiency point of view, because from the spectral efficiency point of view, there is no comment. So it's for sure it goes better. Okay. Then I mean, Bruno told you there might be attenuations, losses, all these kind of things. But I mean, here we can clearly see. So the problem is that we don't know what are the true values of here. So this point could be anywhere. It could also be here. So we need to really to understand. But that's, I mean, to tell you that the SIM can be viewed as a low complexity base station or as a simple implementation of beyond diagonal RIS, which is capacity achieving from the information theoretic point of view under ideal assumptions. But that's the point. So now let's now look at some benefits from some simulation results, and then I will move on. I will tell you ISAC and the other things. But so what kind of gains we can get? These are just some simulation results to put some numbers. This is the application for low complexity base station in a multi-user setting. The scheme I've already showed you. And here, I mean, what kind of model we utilize for this propagation between the layers? We use the Rayleigh-Sommerfeld diffraction model, which is the simplest one to be utilized. It's not the most accurate one, but it's the simplest one. It accounts for the propagation losses that basically there are between the layers. And also one important thing, there is this cosine, which is called obliquity factor, that tells you that the power that is received by that guy over there depends on the cosine of the angle. This ensures that when the guy is very far, you don't get infinite power, okay, when the surface goes to infinity. That's a physical factor that needs to be there, otherwise the model is not consistent. Also because the layers are very close to one another, so you cannot use a far field model. You need to use near field models to deal with this stuff, okay? So the problem is the usual one in this case, maximize the sum rate subject to individual constraints for the SINR of the users, then the cascaded channel and the usual parameters. Okay, now these are transmission coefficients. Huh? So long story short, we applied the projected gradient method to solve the problem. Fan has already told you this in another context. So the concept is simple. You need to compute the derivative of the objective function as a function of the variables. You update, I mean, the variables of the iterations, and then you project on the physical set. Okay. Now, these are the results, the sum rate versus the number of RF chains that we have. We compare two schemes, zero forcing in blue and the SIM in red. So what we can see from here, we can see that if we have 4 RF chains for all the schemes, SIM can double the rate, the sum rate, but you need to have 50 or 100 unit cells for the configurable elements on the surface. But the number of RF chains is the same. If you want to have the same performance with zero forcing, you need to have 7 RF chains. So that's essentially the trade-off that we have in this specific example. So you can definitely reduce the number of RF chains, but you need to play with the number of reconfigurable unit cells. That's the typical trade-off that you can find. Then this shows you the sum rate versus the number of metasurface layers. And you can see that there is a saturation effect. So you cannot increase the number of layers as much as you want, because there is attenuation at a given point. I mean, you're going to lose something, okay? That's expected. So there is a saturation effect. And this is an example that shows you the sum rate versus the number of reconfigurable elements per layer. And you can see that, of course, the more the elements, the better your beamforming capability, and you get better performance. Here, if there are experts in electromagnetics, so these results are obtained without taking into account mutual coupling and other things. So that's very optimistic. Yes. Okay. So if there are experts in antennas, etc., so that I want to stay very grounded and not to claim this infinite increase of the performance. Okay. So we expect something there that is going to happen. Okay. All right, so now another nice application is really to show you the capabilities of this device is imagine that you have this structure also at the base station, and then you have a region, an area, and you want to create a kind of many points where there's a very a lot of power there. So you want, for example, to do something like this. Imagine that there are some users or data street, and you want to illuminate that street, that trajectory, while you don't want to waste power elsewhere, okay? Well, we try to tackle this problem by solving this sort of optimization problem. So maximize the transmission coefficient of the SIM such that you map the received power with your target, minimizing basically the sum of all the powers. The received power, I'm not going to show you the formula because it's the numerator of the SINR that I showed you before, okay? So long story short, here is very clear the impact of the layers. This is what you get with one layer. So you are not able to focus the power as you want because the capability of each layer is not that much. But if you keep increasing the number of layers, you can start seeing that your beamforming capability increases. So if you are asking what is the gain of having the many layers with respect to one single layer, this is a clear example that shows you the gains of multi-layer versus a single layer. Of course, I mean, you don't need, you cannot put 100 layers because if you talk to a company, and I was approached by a few companies, the problem is that they tell you, and you can, I don't want to have in front of my PlayStation 1 meter of device that is there. So it's not something that really I want. So you may have 2 layers, 3 layers, then it depends on how far you put them, but now we cannot expect, so many layers. Okay, so now, of course, as I told you, this is something that is pretty exciting me also because I mean, I see this connection between sensing, computing, and communications. I'm primarily a communication guy, so it's also an opportunity to explore something different. Let's put it this way. But I mean, at a given point, you need to be critical with yourself and to say, so is this new or we are copying the past or something like that? So indeed, actually, your colleague, Christophe. So Christophe Calot, those of you who don't know him, is a super expert in metamaterials, one of the best in his field, was professor for many years in Canada, and now is back. So, and actually he wrote a few years ago this kind of paper, analog signal processing, where he was basically pushing the idea of utilizing metamaterials for doing everything in the analog domain. That's essentially what we are trying to do with this SIM. Okay, so now, in fact, the subtitle of this paper was a possible way or complement to dominantly digital radio schemes, which is essentially what we wanted basically to relate. So it's perfectly nice, perfectly put there. Now, why this didn't fly? I don't know. Maybe it's the same called, I don't know, the same problem as machine learning. Maybe there was not the technology at that time. Now there are many of these devices, and maybe this can fly today. We don't know, but that might be a justification. Okay, so now I want to show you an example that is not related to communication, but is related to direction of arrival estimation. So sensing, to show you how this surface can do also this kind of job, and then therefore you can utilize it for ISAC. So this technology is not only a way to do beamforming in the analog domain, but for me, it's a technology that allows you to do really any sort of signal processing operation, possibly in the wave domain. What does it mean? It means that you could have an input signal, and you could fire at the output the first order derivative of the signal, the integral of the signal, or why not the discrete Fourier transform of the signal. Okay, this performing functions in the analog domain is a very hot topic in the field of metamaterials. There are really many people working on that, trying to implement these kind of things, and papers are typically published in Science, in Nature, because they implement this kind of thing. Okay, so the idea is that when you have a DFT, your DFT matrix, it's something that looks like that. With an SIM, what would you like to do? You would like to match your DFT matrix with your end-to-end response of your SIM. So you want to basically make sure that these two matrices are equal. If these two matrices are equal, when the input signal goes through this multi-layer device, at the output, you see the discrete Fourier transform. And you could do that for any function that you want to implement. The DFT is an example because I want to apply it to direction of arrival estimation. Okay, so we did that. The optimization problem is not, I mean, it's not, the formulation is not so complicated, but basically what you do, you try to minimize the error between the function that you want, the target function, and the response of the SIM with a scaling factor there. And we solved basically this optimization problem. At the end of the day, what you have in practice, that you have an input layer that observes the signals at different points in space. The signal goes through the SIM. It computes the discrete Fourier transform, and then at the output you have an array that senses basically the power that at the output of this structure. And based on the sensed power, you can reconstruct the direction of arrival. That's essentially the algorithm. Okay, so you really have an input layer, this SIM, and then you have a bunch of sensors, this receiver that observe the signals, and this is a front view scheme. So at the end of the day, if now you have a target that you want to detect and you want to get the direction of arrival, you can sense the signal on a given grid. You process this signal through the SIM. You output the DFT. So you get the angular spectrum of the input signal, and from the angular spectrum, you have how the power is distributed in the angular domain. Okay, and therefore you can detect the direction of arrival of the signal. Then you can do sensing in that way, target detection. And this is an example that shows you the output. This is the digital benchmark, and this is what you get by applying SIM. The target was at these basically angles, which are the red crosses, and this is what kind of estimate you can get by using a 2x2 receiver. If you change the angles, just to give you another example, but you use a 4x4 receiver, so you increase your resolution because you observe more and more points, you can get even a better estimate of the actual angle of arrival, direction of arrival of your signal. So that's a clear example that you can do beamforming, but you can also do direction of arrival estimation on many other functions that could be applied in the context of ISAC or other kind of applications. Okay. So now let's go now to the part maybe more related really to ISAC, but also the one that anybody asks. So does this exist? So in the sense, is this only transactions, papers, or it's really practice that this exists? So I don't do any hardware. Okay, so I don't have hardware in my lab. So this is thanks to collaborations with people in China who, thanks to a former PhD student who is there, they. In the time that I was not able to go through the review process of the paper, they got the preprint and they implemented it. So how they did it, I don't know. But I was able to go through the review process of the paper. They implemented the things. That's amazing. But okay, so the credit goes to them. But I want to advertise this collaboration, which is with this university, and then I will show you the name. I mean, of all the people who contributed to that. Basically, they built a transmit array, and then they stacked this transmit array, and then they measured the signals and they evaluated this experimental. And then I will tell you how this is essentially done in practice. For the expert in antenna design, that's the unit cell structure, and that's the overall structure of the scheme. Now, long story short, let's go to this is the paper that, as I told you, was actually submitted for publication to Globecom. So we will see what's going to happen, but it's available on archive, so you can have a look. And now we are working on a journal version. So the team is this one. So the head of the team is Robert, who was a professor in the US, now is back to China, and most of the work was supervised by Kai Wan. I guess that many of you know him. It's quite famous in the field. And my former PhD student is Shuai Wenqian. So now the concept is this: we consider this scenario, which is a typical ISAC setting, where we have a target that we want to detect, and at the same time we want to communicate with the users, with some users. And the problem formulation, I'm not going to go into the derivation of the objective function, etc., but just to let you understand. The problem formulation reads that we compute the Kramer-Rao bound for this specific setting scenario with the SIM. So we minimize the Kramer-Rao bound subject to communication constraints, SINR communication constraints. This is the typical constraints for the power, where we take into account also R0 that accounts for the other part. And this is the transmission coefficient of the SIM. Okay, so it's a typical basically for formulation, but we plug into it the model for the SIM for the SIM. So this is the just a snapshot, I mean, of the hardware and the test bed. This is for 2 layers, an example with 2 layers. And this is, I would like to utilize this slide just to tell you that if you want, this prototype works at 5.8 gigahertz, and each element of the metasurface is a 1-bit unit cell. So it's the simplest that you can do, and it's also the reason why the multi-layers can help, because each layer is very simple in practice. Okay. All right, so that's some results. So this is the communication sensing trade-off. So this is the only curve that is obtained by simulations. All the others are obtained with the experimental platform. So here you can see the SINR threshold, and this is the Kramer-Rao. You can see that by increasing the number of layers from 1 layer to 7 layers, you can see that the performance improves quite significantly. Okay. So that's essentially the main idea. Of course, I mean, there is a diminishing return law when the number of layers start being very large in number. But here, maybe we don't see it very soon because we have a 1-bit unit cells. So the layer is per se extremely simple. But we can really see that we can get a significant improvement for joint or integrated communications and sensing as the number of layers increases. So now this is now let's analyze the communication performance and the sensing performance with the experimental platform. So the number of layers goes from 1 to 3, and what you can see lambda over 4, lambda over 2, lambda, etc., is the interlayer distance, so the distance between the layers. Okay, so let's look at lambda over 4. Lambda over 4 with one layer, you have minus 53 dBm, and you reach minus 46 with 3 layers. So you gain quite some dB. Then you go to lambda over 2 between the layers, and you still gain a little bit from minus 53 to minus 49. When you go to lambda, so the surfaces are quite far apart, you start losing because of the attenuations between the layers. Okay, the distance is too large. So the optimization of the interlayer distance is quite important. Okay, that's essentially one of the things. And of course, if you start put this is obtained with the platform. So when it's lambda over 4, you take into account everything. You take into account the coupling and so on and so forth. But with the models, we have not taken into account of that. So here, the multi-port network theory could kick in. You did some study. You have a paper on that compared to the recent and see. And this is basically just a visualization of the same table. So the number of layers on the horizontal axis, the received power on the vertical axis, no SIM, you are below 70 dBm with only one layer. So there is only one thing. So you are gonna go to 53, as we said. And then I mean the blue and red are lambda over 4 and lambda over 2, and the others decrease. That's just a visualization of what I told you already. So the interlayer spacing is important. This is, on the other hand, the sensing performance, when you were just to detect a target. So there is a result that's a bit strange, but I mean over the second row. But if you consider all the others, this is the location of the transmitter that you want to detect. With one layer, this is the error that basically this is not the interlayer distance. This is the number of layers. This is the 4 degrees is the error that basically you have. 2 layers, you have 3 degrees error, and 3 layers, 2.5 degrees with that setup. So you can look at the table if you like, but the bottom line is that by going from 1 layer to 3 layers, you can improve the accuracy of the sensing accuracy. Okay, going from 3.5 degrees in error to 1.3 degrees in error. So this kind of platform allows you also to try to reduce to improve basically the sensing performance in the way that I explained to you before. Okay, and these are basically experimental results. Okay. So now I conclude. I have just 2 or 3 minutes. I conclude. So sorry if I will be using all the time. So if you are interested, these are some papers that have been published on this field. Besides those that I've already showed you, and here I would like to acknowledge the excellent work from Zhang Sheng Han. The pronunciation is awful, but okay, you can read the name. And is a wonderful postdoc working in Singapore with Chao Wen, and he's really I mean doing great. I think that he studied also with Lajos Sanzo before going back to Singapore. And so you can have a look at the papers. And there are not so many papers around, even though the interest is increasing a lot. So now, if you want to know more information about all this is another paper that I would like to advertise. So you can have a look where there is a lot of also about that. The last thing that I want to tell you is that this is not the craziest things that exist in the literature. When you go to metasurfaces, there are even much more crazy things that you can do. And one of the other exciting things is surfaces that are not planar. They are conformal. They can be curved surfaces, but also where the unit cells can move. You have a flexible substrate, and you can optimize the curvature of the substrate to optimize your performance. There are prototypes You can go to the papers, you will find prototypes in the US, the University of Yale and whatever that built that. So I'm not going to go much into these details, but this is a collaboration with NEC Europe in Germany. They are very much interested. They utilize multi-port network theory to optimize this system. And if you are interested, I mean, these are two papers. One is with Zhang Shen with a conventional communication model, the simple one, and this is with a more advanced model done by the colleagues at NEC. Especially Placido Murcia, who's a researcher, and Francesco De Vodi, who are two researchers there, coordinated by Vincenzo Sciancalero. That's all. Thank you very much for having me. It's a great pleasure.
So can I ask if we have any questions? And at the same time, can I ask the guys to start setting the chairs if you can? We have one from the front, one at the back.
Thank you very much for the interesting topic. So my question is, can you comment on the channel estimation complexity as the number of layer increases?
Yeah, that's a very good point. So we do have a paper on channel estimation. It should be here in the list somewhere. Yeah, this one. So we do have this paper, channel estimation for these things, so you can have a look at the details. So the problem of channel estimation with this structure and the channel estimation. So let's put it this way. It depends on how you want to utilize this SIM. If you utilize this SIM as a transmitter, you don't have the same problem as with a conventional reflecting surface, because you are the transmitter, you can send the pilots, you can do everything as you do usually. Of course, the number of variables that you need to estimate is much larger. So it means that the estimation complexity takes more time and so on and so forth. If you utilize this structure as a refracting device that is put somewhere, then you have the same problem as a reconfigurable intelligent surface in terms of overhead. Therefore, if you utilize the same techniques utilized for RIS based on instantaneous CSI, this will never going to work because the overhead is too much. Already for RIS, the overhead is too much if you optimize with the instantaneous CSI. The way to bypass this is to optimize the system based on statistical CSI. And there are results showing that if you utilize statistical CSI, this is called the 2x scale optimization, 2x scale channel estimation. We have this. You see that the overhead is independent of the number of elements on the surfaces. It only depends on the number of users in the system. Okay. Of course, it works for some channels. It doesn't work for all the channels. Okay, so this is basically a short answer. So we have already done something, but the problems for the two applications that I told you are completely different. But yeah, but it's so yeah.
Any other question? Mr. Richard, yeah. We have 3 or 4, I think. Richard, please.
First of all, thank you so much. Super interesting and really, really cool results. I was just curious because at the moment, between the different layers, you just got air. Have you thought of putting some dielectric material between?
Yeah. So that's a very good point. So yeah, we can put some dielectric there. Then I mean, we need to understand the losses, etc. But the comment that I got from people working in metamaterials and physics, it's really try to not to have a hair, but try to have some materials there that allows you to do these non-linearities, but thanks to the materials that you are utilizing. So yeah. So
I guess I was thinking about putting some dielectric material might reduce the losses that you have between.
Yeah, absolutely. So
You can do some
clever optimization, exactly. You can also control these materials that are inside and try to see. But definitely, I mean, with the hair is the simplest way that you can do. But that's a very good point. Yeah.
Thank you. Yes.
I thank you for that. You had some slide on the error angle. I was just curious to know because it seemed to be a pretty high resolution measuring in terms of error. Is that average error or?
No, this
to measure 1.5 degrees. How are you measuring this? I mean,
so this was the. No, I think that we took many snapshots and then we compute the average. Yes, definitely, yes, yeah. And this is the average. This is the average for the different positions. This average here. each value here is obtained by averaging over different channel realizations, etc. So that's that. I mean, the error that you see there is the error for the different positions.
Yeah, I'm just for a single error for one layer. Getting
You mean okay. Sorry.
Fine resolution.
Sorry. So basically, you have your DOA, so your transmitter that basically is there, and we just try to apply one snapshot to compute basically the error at the output of the SIM.
Yeah, but still, I mean,
But
how do you measure 1.93 degrees? That's what I'm, because you're to measure RF
because
energy, the angle resolution, you
uh,
don't have measuring systems to measure RF energy. Even the best, say, electronic warfare systems,
yeah.
we give you maybe 2 degrees or something.
So what we did, I mean, I can tell you what we did. So what we did is the following. Let me see now. I have it here, so I can tell you exactly. Okay. The structure was this one. Okay. So what we did is that you have your signal that is coming. It just goes. You sense basically the signal on a grid. It goes through the multiple layers, and then you sense the power at the receiver. By sensing the power of the receiver, you can get the peaks of this, and based on the peaks that you get, you map it into a DOA. And then you compute the error from this DOA. I'm not sure if this answers you.
That was answered. Okay.
The same question, which I
Just one curiosity related to this example, but do you need here a number of RF chains equal to the number of elements or not? I mean, to sense the received power.
Sense these are basically
These receiving
these are basically sensors. Here we don't really do the.
You don't need an RF
You did an exchange. These are just sensors.
Power
detector.
Yeah.
Thanks a lot, Marco. When you compare the energy efficiency of BD-RIS and SIM, you assume a fully connected architecture?
Yeah.
You have this circuit square in your...
Yes. This is something that we discussed with Edward and with Mohammed. The results that we have, these are essentially for the n times n minus 1 divided by 2. This is basically the number of circuits that we consider. Now, what we would like to do, because essentially, what we would like to do is what the tree that you basically proposed. In that case, I guess the crossing point will be a little bit in another position. So it will be basically different. The main problem that we have with these results, which is basically this is a really parameter dependent. So we cannot make any general conclusion about that. Is that if we have a conventional diagonal RIS, we don't know whether the power consumption of the unit cells will be the same as the power consumption of the beyond diagonal RIS, because the structure of the system is different. No? You said with this beyond diagonal, you need to have this tree. It's a sort of transmit array, so it's more complex, the structure with respect to a reflecting array. So I cannot tell you, I cannot generalize basically the results here, but the results are obtained for n squared divided by 2. So the switching point could be a little bit different depending if we utilize D3, for example. And of course, I mean, it depends a lot on this value here. So this is something that needs to be studied. Now, as far as I know, there is one paper on the power consumption of a RIS, but diagonal RIS for a specific architecture, which is done by Southeast University, and they have a paper about that. But it's focused on the actual metasurface that they have. So even we cannot, I don't think that there is an actual power consumption model for a general metasurface. We need that to make this comparison. This is just a snapshot, an example. Yeah.
Thanks a lot.
Maybe one final question.
Thank you, Marco. Considering a point-to-point MIMO setting with a fixed number of streams to be transmitted from the base station, doesn't reducing SIM reduce the number of RF chains required?
Yeah. So, yeah. So, I mean, of course, I mean, if you want to transmit a given number of streams, independent streams, you need to have that kind of number of RF chains. That's, I mean, I understand. But I mean, the point is that the point is that you also basically want to have let's basically look at this at this way. You are in a millimeter wave channel, and your channel has some characteristics, and you know what your degrees of freedom is, so your spatial multiplexing. In principle, you can transmit those kind of number of independent streams. But then you also want to have some beamforming gain in order to overcome the losses that, for example, you have at millimeter wave, etc. And there are, for example, this solution based on array of subarrays that basically do that. So you have a number of subarrays that depend on the number of streams, plus you have inside you have many antenna elements that give you the beamforming gain. So you may look at something similar, something basically similar here. But in any case, I mean, this concept of holographic MIMO or a SIM with the trade-off between a number of RF chains and number of elements is exactly the same as the typical hybrid base station design. It's exactly the same, but it's done in a different manner from the implementation point of view. Back in the days, it was called the continuous aperture MIMO. 15 years ago, there is a paper that everybody has ignored, and then there is a journal paper, beam space MIMO, which was a journal version of this continuous aperture MIMO, published in a Silomar many years ago. It's exactly the same concept. Yeah.
Okay, thanks again, Marco. So we have about 45 minutes for a panel, so can I invite all the speakers to come to the stage and pick a chair? Yeah, we can take it to the floor.
Yeah.
Okay, guys, can I ask you to have a seat? Please. Here's a present for you. Feel free to take it.
Let's do some kind Okay. You don't want to have
So Marco, you took your microphone up, right?
Yes.
I was gonna ask you to do all the ducting. And so maybe we can share, so we have the other.
Yeah, this is yours. No, but I do have it.
So when we can share, maybe Marco, you can wear yours.
Yeah.
I'll give this randomly. So one chair.
I'm sure.
Man escaped, yeah, he had some, he's doing some work back home, he's been. Okay, so I mean, we have 45 minutes of a panel. I'm trying to figure my questions here. So I have a few questions set up just to kick things off. But I'm hoping we're not going to go through all of these and instead we're going to have a discussion. And so the idea is just to stimulate a bit of a discussion and pick your brains on the future of ISAC, basically. And so again, once again, many thanks to all of you for attending this and putting your brains out for everybody to look at your thoughts. So maybe the first thing I wanted to discuss is what, in your view, are key applications for ISAC most likely to be adopted? Where do you see your research being applied, soonest? And what do you think is more likely to happen? This probably is for the industry, but your academic opinions would be. So maybe I'll start with Stefano, who haven't sit closer to me.
So I leave that because I can say whatever and the other speaker. Okay, from my point of view, okay, there are many applications. I'm not going to listen to them, but the ones that I presented in my book was about the surveillance of the sky in a smart city environment. That could be one topic. If we think of from now to 10 years or 20 years ahead in time, we can